Okay, back to calculus. So, 3 more examples here. Suppose a population of insects increases according to the law of exponential growth. There were 130 insects after the 3rd day of the experiment and 380 after the 7th day. Approximately how many insects were in the initial population? So what we're actually trying to find is that C, right? So we're going to, again, continue to use the model y equals CE to the KT. And we know that after 3 days, there were 130 insects. And that after the 7th day, there were 380 insects, okay? So what we're going to do is solve for C and then substitute in order to find K, all right? So we have 130 is equal to CE to the 3K, right? And we, I guess I can solve here. So 130 over e to the 3K is equal to C. But then I can also say that 380 is equal to CE to the 7K. So 380 over e to the 7K is equal to C. Now I can actually set these equal to one another. So 100, where do I want to do this at? 130 over e to the 3K is equal to, 1 second, I'm going to pause for a minute. Okay, I think this should work, is equal to 380 over e to the 7K. So 130 e to the 7K is equal to 380 e to the 3K. I'm going to divide here, so I have e to the 4K is equal to 380 divided by 130. We've got 38 over 13. So follow me up here. 4K is equal to the natural log of 38 over 13. So K is equal to 1/4 ln of 38 over 13. Then we can write this into our model. So our model is y equals CE to the 1/4 ln of 38 over 13. And now I still need to actually find what C is, so I'm just going to use this 130. So 130 equals CE to the 1/4 ln of 38 over 13. T, I'm just going to do this in my calculator, pause. Okay, I put in my calculator 130 times e to the 0.75 ln of 38 over 13, and I got C is equal to 58.1518. So C is about 58 insects initially, right? That's what we were trying to find, was that initial amount. Okay, let's actually do a problem here with some half-life. This is a pretty common usage of differential equations and exponential growth and decay. If A of t is equal to A sub naught times e to the kt, with k is less than 0, then the half-life of A is ln of 2 over k. So half-life is equal to ln of 2 over k. And this is our model, which you can see lines up with our y equals ce to the kt model for half-life. So a zircon sample contains 4,000 atoms of the radioactive element 235U. Given that 235U has a half-life of 700 million years, how long would it take to decay to 125 atoms? Well, okay, so our model here is going to be A sub final, our final amount, is equal to A sub naught, which is our initial, times 1/2, our half-life, to the t over k power. And this is actually the model used for calculating a half-life. And so t is our millions of years. K is equal to 700 million years. We were given that information in the problem. And when t equals 0, we have 4,000 atoms. And when t equals something, we have 125 atoms. That's what we're trying to find, is this t. How long would it take to get to 125 atoms? So we're going to say that 125 atoms, our final amount, is going to be equal to our initial amount, 4,000, times 1/2 to the T over 700 power. Okay? So 125 divided by 4,000 is equal to 1/32. It's equal to 1/2 to the T over 700 power. Okay. Then I'm going to natural log both sides of this, so I get ln of 1/32 is equal to the natural log of 1/2 to the T over 700 power. Okay. Then I can rewrite like natural log of 1/2 is natural log 1/32 is equal to the natural, how do I want to say, natural log of 1 minus natural log of 2 to the T over 700 power. This natural log of 1 is 0. So we have, and so this is natural log of 1/32 is equal to, this exponent can come out front, negative T over 700 ln of 2. Okay, so then we have ln of 1/32 over ln, I'm going to actually move the negative with it, negative ln of 2 is equal to T over 700. So 700 times ln of 1/32 over negative ln of 2, what a mess, is equal to T. Pause and I'll put this in my calculator. Okay, I entered it in my calculator and I got T is equal to 3,500, and this is in million years. All right, that's how long it will take for this to decay to 125 atoms. Okay, one last example and then we will be done for today. This is a cozy little example. A cup of hot chocolate placed on a table cools at a rate of dC over dt equals negative 0.05 times C minus 75 degrees Fahrenheit per minute, where C represents the temperature of the hot chocolate and T is the time in minutes. If the coffee was at, this is hot chocolate. If the hot chocolate was at 160 degrees Fahrenheit initially, what will its temperature be 10 minutes later? Okay, so dC over dt is equal to negative 0.05 times C minus 75, right? So I'm going to rewrite this. We'll get dC over C minus 75 is equal to negative 0.05 dt. We can integrate both sides. So we have the natural log of C minus 75 is equal to negative 0.05 T plus C, right? So if I take all this to the E power, I get C minus 75 equals, and I'm just going to, now I know that this, to the C power, I'm going to end with C e to the negative 0.05 T, right? So C, why did I use C twice? That was stupid. But C of T is equal to C e to the negative 0.05 T plus 75, okay? Where this C is a constant and this C represents hot chocolate. That was not very bright of me. So C of 0 is equal to C e to the 0 power plus 75 equals 160, right? 160 degrees. So anything to 0 power is equal to 1. So C equals 160 minus 75 is equal to 85, right? So our real temperature calculation is C of T equals 85 e to the negative 0.05 T power. And then what's going to be the temperature after 10 minutes? Well, C of 10, oops, I wrote right, plus 75. Plus 75 is going to be equal to 85 e to the negative 0.05 times 10 plus 75. I will pause and put this in my calculator. All right, I put it in my calculator and I got 126.555. So C of 10 is equal to 126.555 degrees. So C of 10 is about 127 degrees Fahrenheit. And that's it. Hopefully that's enough examples for you to understand growth and decay. If you have any questions, leave them in the comments. I look forward to seeing you in class. Goodbye.